Okay, so good morning, everybody. In yesterday's class, I'm hearing some echo. Okay, yeah, now it's better. In yesterday's class, and also let me just remind everybody that unless I said that you can unmute yourself at any point during my class and ask a question. You can also raise your hand in the Zoom window. If you don't know how to raise your hand, I hope you will figure it out soon. Also, the lectures are on live streamed on YouTube, so I'll share the link. But after a while, I guess people figure out that they are all shared on my channel. Okay. All right. So good morning again. Yesterday's class, I started talking about relativity, and again, since this is a MSc graduate level course, I am not going to go into a great many details about the history of relativity and so on and so forth. But we will start talking about what is known as Minkowski spacetime. And so for that purpose, I started discussing notation, right? So Minkowski spacetime, right, 3+1 dimensions is the structure that is used to describe physics, relativistic physics in our world. And points in this space-time are labeled by 4 numbers, right? T, X, Y, Z. We multiplied T by C to make all the coordinates have the same dimensionality. Okay. Then I introduced this index notation and summation convention for dealing with linear algebra, because we'll be using a lot of linear algebra, right? So the summation convention basically says that whenever you have two repeated indices, it is understood that there is a summation that is involved. So you can take expressions such as matrix multiplication or vector dot products of vectors, or traces of matrices, or multiplying matrices by vectors. All of these can be written in this way without specifying any indices, without specifying any explicit sums. So you don't need to put any sigma sum over anything, because it's understood that since the 2 indices in this expression, j is repeated twice, that means we have to sum over j. Then there is some notation. So for whenever you see lowercase indices I, j, k, and so on from the middle of the alphabet, they will represent spatial indices. Space, so some, like x, y, z. So I, j, k, and maybe k, l, m if needed. On the other hand, when I want to talk about when I use these Greek indices, then I will be referring to space-time indices. So space-time indices go from 0 to 3, 0 being the time coordinate. So we write down the coordinate of a point in space-time as a 4 vector, right? X nu in this way, x0, 1, 2, 3. So this is the time-like component. These are the spatial components. Okay. And now let's say I have 2 different vectors in space-time. Then one is x mu, and the other is y mu. Then when I write x mu, y mu, again using the summation convention, what I'm doing is I'm summing over x mu and y mu. And when you do that, what you get is this minus x naught, y naught plus the dot product of the spatial component, right? So why do you get this minus sign? You get this minus sign because you are in Minkowski space, right? So the same expression can be written using the metric tensor in Minkowski space, which is just a matrix which has one minus component and the other plus component in the diagonal. Okay, so now let me give you some more background in today's class about what this metric tensor is, why we need it, how does it explain the geometry of space-time, and so on. Okay, so please ask if you have any questions. Please ask again. You can interrupt me at any point in time. But do you have any questions so far? And also another thing is that if you don't attend the lectures regularly, or watch them on YouTube in case you aren't able to attend, you will not be able to follow the material. Okay, so please, if you want to follow the material, I request you to be regular. Okay. All right. So questions? Okay. No questions. All right. So what is this metric eta mu nu, and why do we need it? Okay. So in relativity, so this is called the metric tensor, and also there are other words for it. It's also called the Minkowski metric. Okay, or the Lorentzian metric. Why is it called either one of these? Because Lorentz means it refers to Lorentz transformations, right? Now, on the other hand, if I have something like this, let's say delta ij, then this would be the metric tensor. So this is for 4 dimensions. This is for 3 spatial dimensions. This would be the metric tensor, and I would refer to this as the Euclidean metric. Euclidean metric because in 3 dimensions we are using the geometry of Euclid. You could also call it the Pythagorean metric if you wanted to. Now, where does this metric tensor and the associated this expression? So if I write down again, I have some 4 vector. It has components x1, x2, x3, and then let's say I have a small change, okay, in this 4 vector, delta x1 and so on, so forth, right? So what is the distance between these 2 vectors? What is the distance between this point and this point, right? So it's like saying that in 3 dimensions you have a vector A, and then you have some vector delta A, right? So these are 2 points, right? And so this would be A plus delta A. And then I would ask, what is the distance between this point 1 and point 2? So the distance between point 1 and point 2 would be just the length of this vector delta A, right? And this length would be given by, well, I would write it like this, and I would say that this is delta I, like this, delta AI, using the summation convention, right, with a square root. So this is just a Pythagorean length of the vector. Another way I could write this is as square root of delta ij, delta ai, delta aj. So I'll just put this in brackets to denote the fact that these are independent. This is one whole expression, delta ai. So this is delta ij. What is delta ij? Right. This is just a diagonal matrix 1, 1, 1. Right. So this is the usual length of a vector. Okay. Again, this is nothing surprising. We know this. Of course, this is the expression for this metric tensor in Cartesian coordinates. Right. Now you could be in polar coordinates or spherical coordinates or cylindrical coordinates. So in those different coordinates, what would happen is the expression for this metric will change. Okay. So I'll talk about that at a suitable point in the future. Okay. So now this is the Euclidean distance between two spatial points, right? But we want to talk about points in space-time. So these are the 2 points in space-time. Okay. So what is the distance between these 2 points? So the distance between these 2 points in space-time. So I can write it like this: distance between x mu and x mu plus delta x mu is the length of this vector delta x mu, right? And what is the length of this vector? How will I write it? I'll write it like this: delta x mu, delta x mu, like this. So now here there is one thing that is happening, right? Which is that in the first expression, I have written an index which is raised, and the other expression I have written an index which is lowered. So what is the meaning of this lowering and raising? So if I have any tensor, any object, any vector, it can have indices which are either raised or lowered or some combination. So for instance, if I put an index here, this is a raised index. All right. If I put an index here, this is a lowered index. Okay. So what is the meaning of this raising and lowering? So given any vector with indices which are, let's say, in the lower position, I can raise this index by multiplying by eta mu nu, like this. Okay. What is this eta mu nu? This eta mu nu with the indices raised is the inverse of this eta mu nu with the indices lowered. Okay. So let me write that here. So I have defined this eta mu nu, and this is diagonal minus 1, 1, 1, 1. Then eta mu nu with the indices raised, well, it's the inverse of the other one, of the first, for this eta, but the inverse of this matrix is the same, because you can see that if you multiply these two matrices, you get the identity. And how would I multiply these two matrices? Again, reminder about how to use the index notation. If I have two matrices, A and B, I multiply them to get a third matrix, C. How would I write the element ij of C? I would write it as aik bkj, like this. Right? Now this index k is being repeated here. So I am summing over this index. But now I have these matrices with indices lowered and raised. So how do I work with such objects? So let's say I have two matrices, let's say, which are in four which are four-dimensional matrices. So in 4D, now, so in 4D, I would write like this. I would say, so my objects are 4 by 4 matrices, right? 4 by 4 means your indices run from 0, 1, 2, 3. So that means I should use what kind of letters? Greek letters, right? Mu, nu, alpha, beta, and so on. So I'll use C alpha beta like this. Now I can write it, I would write this product in the following way: A alpha gamma, B gamma beta, like this. Okay. Now what is this? What is going on here? I have this repeated index, which is gamma, right? But this index on A is raised, whereas this index on B is lowered. Okay. So why is this happening? Why is it being written in this way? Well, another way to write this is the following: A mu B nu beta, like this, and then multiplied by eta mu nu, like this. So what does this eta mu nu do? When I put eta mu nu in this way, it takes the mu index over here, right? So if I take, for instance, alpha mu multiplied by eta mu nu, what does it do? It takes the mu index and it raises it to give me a different index in the raised position, which is mu. Similarly, if I have something like this, A alpha nu with two raised indices, I multiply by A eta mu nu. What will this do? This will take, my alpha index will remain untouched, but my mu index will be lowered. So this is called raising and this is called lowering. Okay. So all right. Now, so what happens if I take a vector and raise or lower its indices? So let me take a vector x mu. It has some components x0, x1, x2, x3. Okay. Now I raise the index. So I write x mu with the index raised. How do I raise it? I multiply it by eta mu nu x mu, like this. Right. So nu is a repeated index. It's contracted over. What do I get? Well, this is minus 1, 1, 1, 1, and x. This is x0, x1, x2, x3. So that gives me that x mu with the indices raised will have the following components: minus x0, x1, x2, x3. Okay. I'm just writing it in this horizontal way, but you should keep in mind that this is a vector. So you should, when you think of vectors are column objects. Okay. So what has happened in the process of raising my indices? My first component, the time component, the sign of this component has changed. Right. So here, whatever the sign was here, I have gotten a negative sign. Okay. Now let's say I want to calculate the length of the vector x. So what is the length of the vector x? So I would say that this x, I would say this vector x length I would write it like this: x mu, x mu. Now this can also be written as eta mu nu, x mu, x mu. One of the benefits of this index notation is that you don't have to worry about the order of the product of the items in your products anymore. So for instance, when I talk about matrix multiplication, when I talk about this, right, you know that C is equal to AB, A product B, but if you have two matrices, then B product A is not equal to A product B, right? So the order of these expressions matters, right? Similarly, let's say I have something like this. I have, or I have the product of three matrices, A, B, C. Then this is not equal to ACB, and this is not equal to CAB, right? Because matrices in general, they don't commute, right? If I take two matrices and multiply them, I get a different answer if I multiply them in the reverse order. But if I write down the same expression using the index notation, then what happens? So now let me write the product of A and B. Let's say this is some matrix C. Then I would write the components of C as Cij, Aik, Bkj, like this. Now in this expression, these are just numbers. This is a number and this is a number. This is the ikth element of A. This is the kjth element of B, right? So I can also write this expression as dkj ik aik. And this is perfectly fine because now all I'm doing is exchanging the order of multiplication of two numbers. I can always do that, right? Whether complex or real, it doesn't matter. Similarly, and but it's understood that I am summing over k, right? So if you have a sum like this, let's say if I have a sum over I is equal to 1 to whatever 3, let's say ai bi. I can also write this as I is equal to 1 to 3 bi ai, right? It doesn't change. The expression remains the same. That is what is happening here. Then if I talk about the product of three matrices, let's say A, B, C is equal to D. What would I say? I would say Dij is equal to A, I. Now I will have to use. So by the way, these indices which are repeated, for example, K is repeated. These are called dummy indices. They're called dummy because, well, instead of K, I can use any index. It doesn't matter, right? Because in this expression, when I have this repeated index, that repeated index basically goes away, right? So it like just works quietly in the background. It's like a, I don't know, like a dummy. So now here I have to multiply A with B with C. So I need two dummy indices. So let me use K, Ik, then Km, and then C times Mj. So what is happening here? These two indices, they are repeated. So when we have repeated indices, when we have repeated dummy indices, we say that they are contracted. Again, we have this index M, which is repeated. So these two indices are also contracted. Contracted just means summed over. So Dij is this matrix. So it's this element of this matrix. And when I this is how I would write the product, right? If you want to write it out using the summation of full summation expression, how would you write it? You would write it like this, right? Aik bkm cmj. This is how you would write down the product of three matrices, right? Now in this expression, if you can, I can also write this expression as cmj bkm. The expression remains unchanged because cmj is just a number, bkm is just a number, right? The only thing that matters is that this m is being contracted with m and k is being contracted with k, right? So again, I can forget about these sums over here. I'm just putting that sum in to remind you that, well, there is a sum involved, okay? All right. So now coming back to the case of our 4 vectors. So in 4 vectors, what I told you is that if you raise or lower an index, you get a minus sign on the first index. Now you might ask, why am I not raising and lowering indices when I'm writing this I and k over here? The reason is that these are all spatial indices. I'm working in with things which don't have any time components. So for vectors which are spatial vectors, for a vector x, which has components xi, x1, x2, x3, right? How would I raise or lower indices? I would raise an index by using my spatial metric, right? So what is my spatial metric? My spatial metric is delta ij, like this. But when I multiply this delta ij, what will I get? I will just get x1, x2, and x3. Right? It's because this is just the identity matrix. So the identity matrix multiplied by this vector will just give me the same vector, right? So there is no change between the vector with the lowered indices and the vector with the raised indices. It's the same vector. On the other hand, if I take x mu with the raised indices, I get a negative sign on the first component. So this is not the same as x mu, right? So when you raise and lower indices for 4 vectors, you have a difference. That is why it makes sense to raise and lower. Otherwise, it wouldn't make any sense. Okay. All right. So now let's again look at this length of a 4 vector. What is this length? And what is the meaning of this length? It has some physical meaning. So let's write that down. So what is this? This will give me minus x0, x1, x2, x3. And the other one is x0, x1, x2, x3. What does this give me? This gives me minus x0 squared plus x1 squared plus x2 squared plus x3 squared. So this is the length of a 4 vector. Right? And there is a big difference between the length of a 4 vector and the length of a 3 vector. If this is a 3 vector, let's say u is u1, u2, u3, and I take the length of this 4 vector. So I should write this as length squared. I will get u1 squared plus u2 squared plus u3 squared. Now these are all squares, right? So these are all positive numbers. So this is the sum of 3 positive numbers. So that means this will always be greater than or equal to 0, right? But if I look at the length of my 4 vector, so this is a 3 vector. For a 4 vector, the length, the squared length, not the length, but the squared length, which is this quantity. You see, this is these are 3 positive numbers and this is 1 negative number, right? Because x naught square is a positive number, but there's a negative sign here. So if I take the sum of a negative number and 3 positive numbers, I can get 0. I can get 0. I can also get less than 0, or I can get 0, or I can get greater than 0. Right? So these are 3 possibilities. Okay. What is the meaning of these 3 possibilities? When the length of the vector is greater than 0, I call it a space-like vector. When it is less than 0, I call it a time-like vector. And when it is equal to 0, I call it a null or light-like vector. Okay. Now, what do all these things mean? I will explain one by one. So we will be using space-time diagrams a lot. So let me show you what a space-time diagram looks like. It looks like this, right? You could also draw a second axis, let's say y, but then there is no room for the third axis, okay? Because we are in three dimensions. In 3 dimensions, I don't know how to draw a 4-dimensional picture. So normally what we do is we just forget about 2 of the spatial dimensions, right? For most purposes, that is okay. So this is my, so I am some observer, right? I can label points with a spatial coordinate and a time coordinate. Okay, now what is the meaning of these, of a point here? So if I label a point over here, if I have a single point, let's say I write it as, and from henceforth, this C I will set equal to 1. So I will just write C, okay? So that's just a choice of units. I can always make that. So let me take a point. Let's say I label it like this, T1 and X1, and I have another point over here, and I label it as T2, X2. So what are these points, right? Well, these points are what are known as events. Any point in space-time is called an event, right? What is an event? An event is a snapshot in time, right? When you take a photo, right? So if you take a photograph of anything, you are capturing events. If you make a movie, you get a sequence of events, right? So let's say that you have, okay, let's say that you take a selfie, right? We'll use this terminology to explain what is going on, right? We are living in the selfie era, so let's talk about that. Okay. Now my origin can be anywhere. Okay. So let me say that with respect to the origin, I'm located at some point x is equal to L naught, right? And I take a selfie at time, at the initial time, whatever that initial time is. Okay. So this could be, let's say 10 a.m. Then I don't move, right? I'm doing some work on my computer. Then after another half an hour, I take another selfie, right? What happens? I have not moved in space, right? But I have moved in time. So my first selfie event is associated with this point. This is the second selfie, right? Third selfie, let's say at 11 a.m., right? Why are you taking selfies every half an hour? Who knows? Who cares? It doesn't matter, right? You can do that. People do all sorts of crazy things these days. The point is to show you that each of these selfies is an event, and each event is a point in this space-time diagram. So if you draw a set of events like this, right, what does it represent? It represents the world line. So this is called a, if you draw this line here, this is called the world line of a particle or an observer or anything else. Okay. So alternatively, let's say that I am sitting in my room, okay, and I have a table that's located over here, and I have a chair that's located over here, okay. Oops. And let's say I have a water bottle that's sitting over here at different positions, and they are all at rest with respect to me. How would I draw the word lines of these objects? This would be the word line of the table. This would be the word line of the chair. This would be the word line of the bottle, right? They are all at rest with respect to me in my frame of reference. Now let's say that I look outside the window and a bird flies out past the window. Okay? How would I draw the line of that bird, right? Well, would it be a vertical line, straight vertical line? No, right? Tushar, you wanted to say something?
So this space-time diagrams are like a frame of reference for a particular observer.
All right. Absolutely. That's exactly what they show. They show space-time as seen by a particular observer. Okay.
Okay.
So if I want to show this bird, right? So the bird appears in my view as it crosses the window. Let's say the bird shows up. This is a bird, by the way, right? The bird shows up at this point, x1, right? It flies to the other end of the window. So the other end of the window, let's say it is located at x2. This is x2, right? And in between, what is the trajectory of the bird look like? It looks like this, right? This is a bird, by the way. right? When you draw like a sunset, how do you draw a bunch of birds? You draw them like this, right? These are birds. So this is a bird which goes from one end of the window to the other end. The horizontal direction tells you the spatial displacement, and the vertical direction gives you the time displacement. So this is delta x and this is delta t, right? So what is the slope of this line? The slope of this line, I'll write it as m. This slope is what? This is delta t by delta x. And remember that we are putting delta t in units of light. Okay, so that means there is a c that is hiding over here. Always keep that in mind. Now what does this quantity become? This quantity just becomes c divided by v, right? Where v is the velocity of the bird, delta x by delta t. This quantity we write as 1 by beta. So if you have the velocity of some object, I divide that by the speed of light, I get beta, right? This is we'll use this all the time. Now, what can you say about the slope of the line? The slope of this line, if v is greater than c, right? What can you say about the slope? Is the slope greater than 1, less than 1, or equal to 1?
Less than.
Less than 1. V is less than c. The slope is greater than 1. And if v is equal to c, the slope is equal to 1. So what does that mean? It means that whenever I draw, I'll put this c back over here, okay? Because you might not yet be accustomed to working without it, so I'll just leave it there. So whenever I draw a line at 45-degree angle, okay, it's 45 degrees. Let's say like this or like this. Try to make them as parallel as I can, or in the other direction like this, right? So m could also be -1. What do these lines represent? What do these lines represent? Manikant, how should I think of these lines? What are these lines? This line is a bird, right? Traveling at some speed. Yeah.
Yes, sir.
So what is the speed of the bird that is traveling along this line?
Charging ಆಗಿಲ್ಲಲ್ಲಪ್ಪ.
Hmm?
ಇದು ಚಾರ್ಜಿಂಗ್ ಆಗಿಲ್ಲ ಫೋನ್. ಚಾರ್ಜಿಂಗ್ ಆಗಿಲ್ಲ.
So velocity of light.
Here the velocity m is equal to 1. So the velocity is the light, right? So this is something, any diagonal line in this diagram represents light, basically something moving at the speed of light. Okay. All right. Any line which is at an angle greater than 45 degrees, this represents v is less than c, something that is moving with a speed less than c, less than the speed of light. And any line which has a slope less than 1 represents something that is moving with v greater than c. Okay. So again, what does all this have to do with this? Remember that we talked about the length of a vector and how it can be less than 0, equal to 0, or greater than 0. So now let's look at 2 points in our space-time. Let's say this point and this point. Okay. So this point is t1 comma x1, and this point is t2 comma x2. And there is a vector which connects these 2 points. Right? What is this vector? This vector is, how would you represent it? You would represent this vector, let's say like this, delta t comma delta x. It has components delta t comma delta x. And remember, there is a delta y and a delta z also. But these we are setting to 0. We are setting the 2 spatial dimensions to 0 for the time being. Okay. All right. So what is the length of this vector? Instead of delta x, let me call it something else. We call it r, this vector. What is the length of this vector? R, or length squared? Anybody? And yeah, what is the length? Anybody? Kanchan, Tapsi, Sai, what is the length of this vector?
That would be minus delta t square plus delta x square.
So I would say it is minus delta t squared plus delta x.
First term should have c
Yeah.
square.
Right. So I should put c here again. Minus c squared delta t squared, right? Okay. Now let's say that r is equal to 0. This length squared is 0. What does that mean? This means that this is a signal of light. Right? This means that a light signal or something traveling at the speed of light goes from the first point, which is t1 comma x1, to the second point, which is t2 comma x2. Right? So, and what is the length of this curve? Length is 0. Right? But the points are not the same, right? So this is something interesting that happens in this space-time geometry, that even if points are not the same, the distance between those 2 points can be 0. If the distance between 2 points is 0, then I say those 2 points are at a light-like or null separation with respect to each other. Okay. On the other hand, if r square is less than 0, then that tells me that these 2 points are at a time-like separation, right? So if it's less than 0, I say the length of the vector is time-like. So what does it mean when I say that something is at a time-like separation or at a light-like separation? Okay. Now let me draw these are the right. What are these? These are my light rays. Okay, so I am at the origin and I consider any point inside this region. Okay, I consider any point inside this region. Any point inside this region can be connected to the origin over here, right? By a vector whose length is negative, right? So if I take any 2 points in this region, so this is the origin O, and I take any point A, then what can I say about the distance between O and A? The distance will be negative, right? You can see that directly, right? The slope of this line, the slope of the line connecting O and A will be greater than 1. Right? So if the slope is greater than 1, that means that if the slope is greater than 1, that means the velocity associated with this straight line will be less than c. And if the velocity or the length, this term will be greater than this term, right? So you can, so let me just write that down again. This the length of some vector, let's say r. This is the vector r connecting these 2 points is minus c squared delta t squared plus delta x squared, right? And this is equal to 0. This is less than 0, which means that delta x squared is less than c squared delta t squared, right? Which means that delta x by delta t squared is less than c squared, which means that v is less than c. What is v? V is the velocity of the whatever is the signal. I send out a signal from O, I'm such that it should reach the point A, right? How fast should that signal be moving? That signal should be moving at the rate b. On the conversely, if I send out any signal from O, right? I'm at O and I send out a signal in all directions. That signal can at most reach any point in this shaded region over here, right? So if I send out a signal from O, can it reach a point over here? Right? Can the point O send a signal to the point B? What is the distance between this? So let me call this, let's say r prime. What is the length of this r prime? Well, again, let's see, delta t squared plus delta x squared. Now this is greater than 0 because I can see that this line has a slope which is less than 1. So this means that delta x by delta t is greater than c for these 2 points OB. Right? So can I send a signal from O to B?
No, sir.
No. Why not?
So then the speed of the signal will have to be more than c.
Well, the speed will have to be more than c. So all the points in this region, right, are causally disconnected. So the expression that we'll use is, we will be talking about causal and causality, right? So what does this mean? This means that we say that events have causes, effects, and there are effects and there are causes, right? So we say that points O and points A are in causal contact. O and A are in causal contact, meaning that I can send a signal from O to A. It is possible for me to communicate between these 2 points. Are not in causal contact. That means so the points O and B are not causally connected, because it doesn't matter what happens at O. Anything can happen at O. You can have an explosion, you can ring a bell, it doesn't matter. The knowledge of that event at O will never reach the point B. Because the maximum speed at which any information can travel out from O, that maximum speed is the speed of light. But to go from O to B, your information needs to travel at a speed greater than the speed of light, right? So if you look at any point within this red region over here, or on this side, the slope of the line connecting any point in this region to the origin, to this point, is less than 1. That means any signal which goes from O to any point in this region has to travel at a speed greater than the speed of light. So all of these points are causally disconnected from O. Similarly, all of the points within this region are causally connected to O, because a signal can travel from O to any point here. What about the boundary? Well, those points are also causally connected to O, right? Because a light signal can travel from O to any point over here. If I have a point here, a signal moving at the speed of light can always travel from O. Please mute yourself, whoever is unmuted, because there is some. Manu, please, I muted you because there was some noise in the background. Okay. So we will be using in the coming classes, we will be using this space-time diagrams and the length of objects, length of vectors all the time. Okay. So what is the meaning now of this length? We say that this length can be positive, negative, or zero, right? So if it is less than zero, it means the 2 points which are connected by that vector, by this vector, they are in causal contact. Where if the length of the vector is less than zero or equal to zero. And if the length of the vector is greater than zero, then the 2 points are not in causal contact. Okay. So in the next class, which will be, when will be the next class? On Friday. Then I will talk about what do you call it? I will talk about start talking about Lorentz transformations and how Lorentz transformations affect what happens to these vectors under Lorentz transformation. Okay.
Sir?
Yes.
Sir, in the time-like region, I mean, if we consider two events and connect them with a line, and that line is not passing through the origin, is it possible?
No, you're right. So if I consider my so this region is called the light cone, right? For obvious reasons, it looks like a cone. It's not really a cone. It just looks like a cone when you draw it in like this 2 dimensions, or with 3 dimensions, with 2 spatial dimensions and one time dimension. Then it will look like a cone. So you have x, y, and t. Now it looks like a cone. But if you draw the full in 4 dimensions, it's more like a sphere. Okay. Now, the point, what you're saying, I think, is that if I take any 2 points here, the line between those 2 points does not need to be of length, of negative length, right? Is that what you're saying?
Yes, sir. I mean, it will
Right.
it be passing through the origin?
So these 2 points will not be in causal contact, right? That is fine. Because when I draw this light cone, I'm talking about everything that is in relation to this origin. That's it. This everything is defined with relation to this 1 point. Okay. If I want to talk about some other point, let's say I want to talk about what happens with respect to this other point A or this other point B, then I have to draw the light cone of A. And the light cone of A looks like this. What about the light cone of B? The light cone of B looks like this. Right? So any point within this region is in causal contact of A. Any point within this region is in causal contact of B. But all of the points in these regions are in causal contact with O. Okay.
Okay, sir.
So this is not this property of causal contact. It is not a transitive relation. That means that if O is in causal contact with A, and O is in causal contact with B, then that should imply that A is in causal contact with B, right? It's not like that, right? A and B are still causally disconnected, but they are both causally connected to O. I can send a signal to A and I can send a signal to B, but A and B cannot send signals to each other, right? So this diagram picture, so if I just say that in words, it might not make any sense. But when you look at this picture, It's clear from the picture that A cannot send a signal to B. Right? But O can send a signal to both A and also to B. Okay. So as far as reading is concerned, I would suggest that you all start, if you have not already started, to work through STEAM. I will give you a more comprehensive list of guide of items to read in the next class. Okay. All right. So I guess I'll stop here, and I will see you again on Friday. And then starting sometime next week, as I've already told you before, I will be shifting our classes to the 8 a.m. to 9 a.m. slot in the morning. Manikant, will that be okay with you? Do you have any classes from 8 to 9?
No, sir, I don't have any class in 8 to 9.
Okay, so then we'll be having classes from 8 to 9 on 3 days of the week. And okay.
Okay, sir.
Okay. All right, everybody. I will see you on Friday.